So welcome to the first post-keynote talk of the day. Please welcome our speaker, Emma Gordon, who will be talking about evolving code. Enjoy.
So thank you all for coming to this talk. First of all, can I just check everyone can hear me? Cool, awesome. So my name is Emma. I'm a software engineer at this company, Cambridge Medical Robotics, working on a next-generation robotics platform for keyhole surgery. Somewhat more relevantly for this talk, I'm also one of the organizers of a study group for software developers where we look at a variety of topics in computer science. And a year or two ago now, we were looking at machine learning, a range of different techniques you can use there. And one of them was genetic algorithms, which is what forms the subject of this talk. So I ended up taking those and having a bit of fun and seeing if I could evolve some code rather than actually have to write it myself. Having managed to do that, I pretty much instantly became quite concerned about my job security. So if we think back over the course of human history, the way that we live our lives, the kind of work we do, the kind of society we live in, has drastically changed as a result of changes in technology. So previously, a lot of us would have been involved ensuring that we had enough food to eat. The food chain and production took up a vast amount of our time and energy, and we didn't have much time for anything else. So we've been in the field, sowing seeds, harvesting crops. Then we invented things like this, and freed most of the population up to work on other things. More recently, you might have walked into a supermarket, and rather than seeing a load of people at the tills, you now see a row of these. So you might be thinking, okay, well, those are all quite repetitive tasks, kind of things that are quite easy to automate. Skilled jobs will probably be fine. But actually, with the recent advance in technology we're seeing, particularly with the advent of artificial intelligence, increasingly more and more of this skilled work is also coming into the firing line. So if we look back a few years now, so IBM made this. So it's IBM's Watson supercomputer. They originally made it to compete in a US quiz show called Jeopardy. So in this game, if you've not heard of it, the contestants are given the answers, and they have to say what the question was. So in order to be able to do that, you need to be able to understand the words that are said to you, kind of put them in context. You need to have quite a bit of general knowledge, and you need to be able to do things like word association, jump between concepts, kind of think laterally, because some of them are a bit obscure and that kind of thing. So these are the kinds of things you might think, actually a human brain would probably be better at that kind of thing than maybe a machine. But sure enough, they managed to get this to win at Jeopardy and beat all the human champions. And so the way they did that was a combination of some natural language processing to understand the words that were said to it, a big database of knowledge, and then some sort of data mining techniques so they could go and query that, and some machine learning stuff so that they could gradually train this up over time, get it better and better at the solutions that it was coming back with. So since winning at Jeopardy then, perhaps more interesting, they've turned it to some more practical applications. So say in medical diagnostics, where you've got a field with a huge amount of data. You've got all the sort of previous medical knowledge you might find in a medical textbook, constantly new journal articles being published, new clinical trials, studies, records of all patients. It's a huge amount of data that a human doctor can't possibly hope to keep up with. At best, alongside their job, maybe they manage to read a couple of journal articles a week, and they've certainly forgotten the ones they read 10 years ago. This, as soon as a new thing is published, it can go straight into its data banks. It's never going to forget anything that it previously knew about. So it's able to potentially produce a much more accurate diagnosis than a human could, particularly for maybe a very rare condition where that doctor's not come across that condition in their career. We might also apply it to, say, legal work, where again you've got huge amounts of documentation to trawl through, lots of law books, loopholes, results of previous judgments from other trials. Putting together a casework for trial or looking at some legal advice is quite a time-consuming process of sifting through all of that. This, again, with its data store, you can go and query it. And indeed, they're using that to provide sort of legal advice as a service. They've got kind of Watson as the back end, and you've got kind of internet chatbot that you can go on and use, which is quite useful if, say, you might not be able to afford legal representation otherwise. You could also maybe use it in the classroom. So because of its natural language processing, it can understand questions that a student might ask of it, and then go away and provide them with the answer. So now we've got people like doctors, lawyers, teachers, people we think of as really skilled professionals, where machines can now do at least aspects of their job just as well, if not potentially better. So what about software developers then? Like, hopefully, are we okay? Are we needed to write the code that runs this kind of stuff, that maintains it? But as I was saying, it's looking at ways that you could generate that code rather than actually have to have a human write it. And one approach you might take to that is something called a genetic algorithm. So if we illustrate this, okay, let's take a step back. So a genetic algorithm then is a guided random search algorithm, by which I mean, as opposed to a systematic search, when you've got a large amount of data you're sorting through and you start one end and you work your way through until you find what you want, which obviously might take an impossibly long time to run if your search space is massive, or a random search where you maybe go, I'll look over here, nope, not found it, maybe it's over there, no, still not found it, and keep going. In a guided random search, you're going to look at a point, and then based on the value you find there, you're going to decide where should you look next. So say I look over here and I find something that looks sort of like what I'm looking for, I might decide to look in the vicinity of it. Now this makes some assumptions about the kind of space that I'm searching through, namely that it's some way continuous around the points of interest. So I can look at one point and the point next to it should be related in some way. Otherwise that approach just wouldn't work. And in particular, a genetic algorithm is a guided random search algorithm that takes inspiration from biology, namely from evolution, with this idea of natural selection through survival of the fittest. So if you've got some characteristic that makes you more likely to survive, so you're better at running away from like wolves or bears or whatever, then you're more likely to live long enough to pass on your genes to the next generation. And therefore, over time, those favorable traits get selected for. So if we take that in terms of genetic algorithm, then how does that principle work? So if we think maybe about evolving strings, so not programs yet, just a regular text string. So say we wanted to evolve the title of this talk. What I'm going to do first is I'm going to generate a population of random strings. So they'll be with different lengths, different characters, just random strings. And then I'm going to go through and I'm going to evaluate those and see how much they look like the thing that I want to get to. So this is where my analogy of evolution has, to be honest, completely gone out the window, because here we've got an end goal in mind. But we're artificially constructing our fitness function to steer our algorithm to converge on that. So I'm going to rate each of these random strings then. How much do they look like the target? The ones that look most like it, I give a higher score to. I'm going to put them all in order from highest fitness score to lowest, and I'm going to select which ones get to survive and pass on their genes. And a really kind of naive first approach might just say, okay, let's just take the top half, throw all the others away. Then I need to cross these over and combine them. So this step is kind of analogous to you getting half your chromosomes from each parent. So again, a simple solution, I might just say I'm going to take the first half of this string, second half of that one, and just stick them together. Next thing I'm going to do is in the same way as we introduce new characteristics into the gene pool in biology through random mutations of some genes, I'm going to pick a random character in this child string, as it were, and just swap it out for a different one. So what I have now is a population of half the fittest individuals from the previous generation and half their children that I've produced through this crossover and mutation process. I then look through that population and I see, is the target string that I'm trying to get to in there? If so, great, we're done, I can stop. If not, then I need to loop back around. We need to keep going from generation to generation, evolving and iterating until we get to what we're looking for. So let's try that out then, try and demo that for this string example. So what we're going to see here is for each generation, I'm going to print out some statistics about it. So it's going to have the fitness score for the closest match in that generation, the range of fitnesses that we've got, and I'm going to print out the string of kind of the best one that we've got so far. So first of all, you'll probably see that that's one of around about the right length, because in a completely random pool of strings, that's probably going to be your best bet. And then over time, hopefully, we'll see some features fixing the right places, spaces going where we want them, and yeah, we've got to the talk title. How do I go from that to the more interesting example of evolving some program code? So we're going to have some more problems doing that than we had here. So whereas before I could just dump any random characters into a string, and it might not look very much like the target, but it was still a string. If I just dump a load of random characters into a text file, the odds that that's going to be a runnable program are pretty slim. Okay? There's all sorts of rules about syntax, logic. It's just not likely to run. So you might say, okay, I'm going to take the approach of using some templates. I'm going to have this block that looks sort of like a for loop, this block that looks like an if statement, have a fill-in-the-blanks approach, and you can stick them together. And that would work. Your initial generation would probably be runnable code. But then when you start to cross them over, to mutate them, you're going to be back into the same problem again of just they start to be invalid programs. They just won't run. So you might say, OK, I'll make my own language up. I'll have a series of symbols. You can combine them in any order you like, and that'll be fine. They'll be able to cross over, mutate, fine, still be valid. The problem you're going to have there is you're probably going to unintentionally limit what it is that you can program in that language. So you want to be able to evolve code that can do anything you could write some code to do. So in order for that to work, you need to be using a language that is something called Turing complete. So if I take a moment to explain what I mean by that. So Alan Turing then did a lot of research into the theory of computation, particularly the idea of reprogrammable machines. And he invented a mathematical model called a Turing machine to help him reason about those. And what this is, it's an infinitely long piece of tape divided up into a series of cells. And you've got an arrow pointing at whichever cell you're in. And in that cell, and you can move that arrow along. And in that cell, you can put a symbol. And you can read the value of the current symbol, or you can change the value of the symbol that's there. And that's it. And it's quite a simple device, but it can be mathematically shown that anything that is computable, not everything is, but everything that's computable, you can compute it on this machine. And if a language is Turing complete, it just means you can use it to simulate this machine, aka anything you want to program in it, you can do so, as long as it's possible to program that. So that's our requirements then. We're looking for an incredibly syntactically simple language that's also Turing complete. So at this point, I figured, well, that probably already exists. I'm not going to reinvent the wheel. I'll go and Google it. And I came across this site. So this is primaryobjects.com. This is Corey Becker's site. It has a load of really interesting blog posts about machine learning. And one of the projects that she'd been doing on this was exactly this problem, so evolving code. And she'd identified this really simple Turing-complete language to use for it. And this, in fact, only has 8 characters and is pretty much just a model of a Turing machine itself. So in the interest of not repeatedly swearing at you for the end of the talk, I've abbreviated the name slightly. If you can't guess, then Google. But this is just 8 characters. The first 6 are just moving this pointer about, changing the value in the cell, reading it out, writing a value in. The last 2, the square braces, are where things get interesting. This is what gives us our control flow. So the ability to look at a value we've got and make a decision. Do we want to keep looping that around, or do we want to break out the loop? And that's what gives the language its power. So what does some brain F code look like? So this is hello world. So this is your classic first exercise in any new language you want to learn. Just prints hello world to the screen. As you can see, this is pretty esoteric. I don't know about you, but I don't want to write code in this language. My head would hurt. I certainly don't want to debug code written in this language. And that's just a simple thing, not anything complicated. But to a computer, this is just as intelligible as something written in any other language. And to us, it's just a string. So we already know how to create those, how to cross them over, how to mutate them, so we can use all the same techniques again. So let's try and evolve a program in BrainF. So I was going to do hello world, but I realized there probably wasn't enough time for it to converge on a solution in the time left in the talk, so we're going to go with a slightly abbreviated hi. Right? And what we're going to see printed out is we're going to see the output of each program in that generation, and then the program code for just the best one. And we're going to have a few new problems here that we didn't have before. So we might have an invalid program. So whilst BrainF has very few syntactical rules, we do still need those square braces to match up. We might have a valid program that never ends. It might be stuck in an infinite loop. So we need to have a cutoff point by which we say, probably not going to finish, let's time it out. We also, unlike the model of an infinitely long tape, computers don't have an unlimited amount of memory. We're going to have a finite bit of memory, and our program might go off the end of that. Again, if that happens, we need to notice, record it as an error. So for any of those cases, I'm going to give it a very low fitness score and quickly weed them out, so they'd be selected out for the next generation. So what we see here is we got pretty close pretty quickly. We're already down to 2-character words, quite close there. But we don't seem to be getting any closer. Why is it so quick to get there and taking so long to get any further? So the reason for that is, unlike with the string evolution, the thing that's fitness we're scoring and the thing that we're evolving are not one and the same anymore. So we're evolving the program, but we're scoring the fitness in the output. And whilst the output might be quite close, the actual program might still be some way off. So to help it get out of those sort of local minimum that's stuck in, we need to help it a bit. So we've increased the range of mutations that we allow here. So rather than just replacement, you can insert characters, delete them, and when you replace, rather than just one character, you go over the whole string with some probability and replace each one. Similarly with selection, if we just selected the top half and threw the rest away, we would really quickly dive towards what looked most promising on the first generation and ignore other avenues of interest that might ultimately lead us to the solution that's over there. So we need to change our selection mechanism. And we're going to do something called roulette selection. So imagine a big wheel divided into wedges for each individual in the population. The higher the fitness score, the bigger the wedge. And so when I spin a spinner on it, it's more likely to land on those higher fitness individuals. They're more likely to be selected, but the others still have some probability of getting through. So hopefully then, this will get to the thing that we want. So what you might also be noticing is some of these programs quite suboptimal, lots of pluses followed by lots of minuses that pretty much cancel each other out, and you almost may as well not have bothered. Obviously, if a human was writing that code, we would do something more useful. The other thing is that whilst this might just be a program to output some text output, more interesting things have been done. So I was just doing this for fun, so I kind of stopped at this point. Corey, who I mentioned earlier, she took it further, so she made some more computationally interesting programs, things that would generate the first few Fibonacci numbers, that would take input from the user and add numbers together, that sort of thing. You could also take other approaches. So this is evolving the program code. You could evolve the abstract syntax tree of it. You could not use genetic algorithms, try using neural net. Other approaches are possible. It's nonetheless quite an interesting one. Random demos. Awesome. So yeah, I thought that was quite cool, getting that working. If you're interested to take a look, the code is all up on GitHub. So yeah, I'd just like to say thank you for listening to the talk. Thank you to the organisers for putting on a great conference. And yeah, I don't know if we have time for questions or not. But.
So we do have time for some questions. Anyone? Anyone? No one? Maybe I have one. What's the most impressive thing you've seen done with algorithms like these? So you mentioned like Fibonacci numbers and stuff. Is there anything like?
Yeah, so I think for evolving code, I was most impressed by the Fibonacci ones. For genetic algorithms in general, they used quite interesting in scientific areas. So anywhere you've got a kind of continuous search space. So molecular self-assembly is one I've seen it used where you can't really model that. There's too many things going on. Whereas if you use this as a search algorithm, you can find some interesting patterns and so.
Oh, we have one. This ought to be interesting.
Yeah, hey, fun talk. Did you ever use like genetic algorithms to like improve an algorithm you use like in the real world on a daily basis? For example, like cooking coffee and like trying different water temperatures and stuff like that? Or is it only like scientific stuff that's pretty much useless out of the scientific community?
Yep, great question. So I personally haven't used it for that, but it is one of the main use cases actually of genetic algorithms is taking a model that it pretty much works and fine-tuning all the different variables like you were suggesting. So there's a few different things you can change. You can try all the different settings by searching through that space with your genetic algorithm. That's where it's quite often used.
Any more? If not, thank you, Emma. And we'll get ready for the next talk.